Disasters have caused great damage throughout the world, and even now, they could strike anywhere, unexpectedly. The ImPACT Tough Robotics Challenge aims to develop tough robots that can work under extreme conditions to gather emergency information, rescue people, carry out restoration work, and implement preventative measures. The field evaluation forums have been held regularly in the past, and it is now the 6th time for it to be held, with numerous cutting-edge technologies being gathered at the Fukushima Robot Test Field, currently under construction. As well as earthquakes and tsunamis, fire is one of the most dangerous forms of disasters. Indoor fires normally involve firemen with hoses entering buildings to put out fires, but this is extremely dangerous. To support these missions, Dragon Firefighter, the world's first flying fire extinguishing hose robot, was developed. The most important characteristic of this robot is that it flies using the power of its jets of water. The hose has 4 nozzles, and the directions of the jets of water are controlled to propel it through the air. Great lift is created by minimizing the loss of pressure, and a mechanism of wires and rotational dampers has been implemented to control vibrations, resulting in stable motion. Its direction of flight can be changed freely by controlling the nozzles, allowing the fire origins to be directly extinguished. Efforts are underway with the ultimate aim of deploying the robot to put out fires in high-rise buildings by making the hose longer. Rubble that is created by disasters comes in all shapes, with numerous nails and other sharp objects scattered everywhere. Robots are required to grasp such pieces of rubble with unpredictable shapes as they go about their work. A flexible hand with a bag structure, the OmniGripper, was developed to overcome this problem. After enveloping an object, the air is sucked out to solidify the powder inside the bag, allowing it to grasp the object. It requires no complicated maneuvers or positioning, and it can easily grasp all kinds of objects. This hand was covered by puncture-proof fabric, making it more suitable for practical use by allowing it to grasp sharp objects. It is now capable of turning sharp, broken valves, which was impossible until now, and even grasp barbed wire for the first time in the world. This technology will be useful not only during disasters, but also at factories and in everyday life. It will enable fast and easy transportation and assembly of parts. Survivors may become trapped under collapsed houses. 72 hours is the time limit for their rescue, and there is no time to lose. A thin serpentine robot called Active Scope Camera crawls into tight spaces to find survivors. It uses ciliary vibration to move and air jets to levitate its head, and relies on the sense of touch to feel its way through the tangled rubble. It is easy to lose the robot's position inside the tangled rubble of a collapsed house. Images from a camera are used to create a 3D map. The images change too quickly inside the rubble. A high-speed camera is used, and the system is equipped with a function in which frames of shorter intervals are added to allow recovery whenever the matching fails. This enables the creation of maps in real time of the inside of the rubble. The ability to find a search target automatically is an important function. When the target is designated, the robot automatically identifies it in recorded images and displays its position. There are dangerous places inside plants. Thick serpentine robots are able to carry out inspections in such places. This robot can go places that conventional robots can't, such as moving up and down ladders. It can even climb sloping ladders. It moves across rubble by wriggling its body. It can also move through pipes and ducts. It has a rubber cover for protection and to make it waterproof. This Serpentine robot is covered by flexible, tactile sensors. The sensors are made of conductive rubber, and they allow the robot to ascertain its surroundings through the sense of touch. The use of numerous sensors tends to increase the amount of data too, but the sensors developed this time only transmit information on the center of gravity and force at the point of contact. This suppresses the amount of transmitted data. The wheeled Serpentine robot is another type of thick serpentine robot. It relies on its length and thinness to enter tight spaces and uses the OmniGripper to carry out its work. The head of the robot is controlled by camera images, its body shape, and information from tactile and proximity sensors. Controlling the head allows it to move over steps and obstacles to carry out its inspections. It is dangerous for people to operate construction machines from on board at disaster sites, but delicate control is a challenge for remote machines. This remote-controlled construction robot has a distinctive double-swing, dual-arm mechanism that combines the power of construction machinery with the delicate control of the human hand. It is controlled using a bird's-eye view image taken from a wired drone and another image virtually generated from multiple cameras installed on the robot. The forces and impact that are exerted during the operation are estimated in real time by measuring the pressure in the hydraulic cylinders and by an accelerometer attached to the arm. A 6-axis haptic device allows the force information to be fed back to the operator. There is no need for sensors on the hand, ensuring reliability and durability. A demonstration was carried out to lift the roof of a collapsed house, prop it up, and clear a path for rescuing the survivor. Moreover, infrared images superimposed onto visual images allow work to be carried out regardless of environmental conditions, such as the presence of fog or smoke. There are places inside plants that are dangerous for people to work in. Legged robots can replace people for carrying out inspections in such high-risk places. In this experiment, the robot uses its entire body to climb over a high step. Commands are given out in accordance with 3D information gathered from sensors. And it successfully goes over a step that is higher than the length of its legs by pressing its body against the step and maintaining its balance. The robot then detects a valve using the sensor array on its back. It takes on the challenge of opening a tightly closed valve using its hand and no other special tools. Operability and precision are achieved at the same time by adjusting the gain level of commands in accordance with the objectives. Rescue canines play an extensive role in rescue operations during disasters. To make effective use of them, it is important for their handlers to monitor their status in real time. Cyber rescue canine suits attempt to bring out the full potential of rescue dogs by sensing their activities. Rescue canines are given cyber rescue canine suits like this one, which transmits data from a camera, microphone, GPS, and inertial sensor to allow remote monitoring of the status of the dog and what it is doing. A record of the dog's motion and behavior is displayed on an aerial photograph of the site. Analysis of the inertial sensor data shows the dog's behavior, such as whether it is running or barking. A function that automatically identifies the personal effects of victims from camera images gathers information on a terminal regarding what was discovered, when, and where. Personal effects to be identified are registered immediately on site. This allows the discovery of a survivor. Unmanned aircraft, such as drones, are particularly useful for gathering information during disasters. In recent years, they have been used often, but the problem was that they couldn't fly in strong winds. This newly developed aerial robot does not rely on the rotational speed of its rotors to control its orientation, but does so by changing the pitch of its rotors, allowing its movement to be controlled more quickly than in conventional drones. As a result, it is capable of stable flight even in situations where strong air currents create vortexes. In disaster-stricken areas, mobile communication networks do not work. Multi-stage, multi-hop relay stations can connect aerial robots to transmit information over long distances. Using the newly allocated 920 MHz band allows quick switching of the relay path to ensure uninterrupted communication. Drones were said to be unsuitable for sensing sound because of the noise they make, but technologies are being developed to overcome this. A microphone array and auditory processing technology can allow voices on the ground to be heard and their direction ascertained over the noise of the aerial robot. It can even detect the voices of people trapped under collapsed houses. The Remote Sound Source Localization Aerial Robot was developed by combining this technology with multi-hop wireless communication. During disasters, transporting supplies is another important mission. This robot arm allows goods to be delivered while flying. It doesn't need to land. Its center of gravity is not affected by the motion of the arm. It maintains its posture even when the drone moves. This year, the Field Evaluation Forum, held at the Fukushima Robot Test Field, featured a number of world-first and best-in-the-world technologies. The event was attended by overseas disaster response organizations, and it is hoped that innovation stemming from the Tough Robotics Challenge will spread throughout the world. For more safety and security throughout the world, ImPACT.